In this presentation, we're going to discuss Betz's theory. We'll talk about the airfoil, the lift-to-drag ratio, and we will talk about aerodynamics too. Albert Betz was a German physicist. In 1990, introduced a theory according to which we can calculate the wind power that is caught by the wind turbine. If we place an obstacle in an airflow, the obstacle slows down the air velocity. And if it is a wind turbine, behind the wind turbine, downstream of it, the wind velocity will be lower than before the windmill. Here we have the speed V2, which is comprised between 0 and V1. But the two extremes are impossible, because if V2 is equals to V1, it means there is no wind turbine, there is no recovered energy, and if V equals 0, the windmill cannot rotate. No energy is recovered. Betz's theory consists in finding what is the exact wind value behind the windmill in order to recover maximum power. We can also notice that because of flow conservation, the input flow is the same as the output flow. The virtual wind tube's area increases from the upstream to the downstream, and it has the bottleneck, the shape of a bottleneck. Betz's theory allows to obtain a maximum power. Betz's theory indicates that in order to obtain the maximum power on the rotor, the wind behind the windmill should be 1/3 of the wind before the windmill, which gives us a maximum power of approximately 16/27 of the wind power, 0.59 times the wind power, Betz's power. An ideal windmill should be able to recover only 59% of the wind's power. In summary, when it approaches a windmill, will slow down from V1 to 2/3 of V1, and at the back of the windmill, it will be 1/3 of the upstream power. So we can capture maximum power in an ideal windmill. Betz's power, 0.59 times the wind power, half of rho SV1 cubic. Surface will increase progressively from the upstream to the downstream area, and we see the bottleneck effect. Just so that you understand, we have drawn here graphs of the wind power and Betz's power for a surface of 1 square meter with a mass volume of 1.25, and when the wind changes from 1 kilometer per hour to 100 kilometer per hour, we see that the wind power changes by from a few milliwatts to more than 13 kilowatts. Betz's power, 0.59 times the wind power, will vary from a few milliwatts to approximately 8 kilowatts, which would be enough to supply power to one house if the windmill is perfect and the wind blows permanently at 100 kilometers per hour. Now, let us compare an urban windmill with a power windmill. For a wind at 70 kilometers per hour, we calculated Betz's power. If the two windmills are perfect, the urban wind mill with 1 square meter of surface could recover 2.75 kilowatts. If we have a big power windmill with a 30-meter long blade, we would have 7.8 megawatts of power, enough to supply power to more than 1,500 houses. Next question. Why do the blades rotate? There are 3 types of windmills: horizontal axis and vertical axis. All the horizontal axis windmills function according to the airfoil principle. And also the Darius vertical axis windmill operates the same way. However, the Savonius system with a vertical axis is based on the differential drag principle. Before I explain the airfoil notion, I would like to spend a few seconds on Bernouilli's law. In a watering hose, the flow conservation principle says that the flow is the same along the tube. If the cross-section is the same at input and output, the same quantity of water will come out. But if we pinch the tube, we reduce the cross-section and we increase the speed. Bernouilli's law states that in a current line, total pressure is constant. Total pressure is the sum of local pressure, small p, and dynamic pressure, half of rho SV square. If this sum is constant, small p plus a constant speed, if the speed increases locally, pressure decreases. So where the tube is pinched, there will be low pressure, a vacuum. This is the whole principle of the Venturi tube, a tube in the middle of which there is a smaller cross-section. The speed will increase and a vacuum will be created in the middle. If there is a small hole there, there will be suction. A few domestic applications of the principle, the Bernouilli principle. For instance, if we have a perfume vaporizer, if we push the pump, the speed in the horizontal tube increases and there is a vacuum bringing the perfume up. We find the same law in static extractors for chimneys. Due to the shape, there is a pinching in the middle and the wind that blows in the tube accelerates in the middle, creating a vacuum that drags the smoke gases out. And the same goes when you have a hot water shower. Locally, the speed increases, thus creating a vacuum, and the vacuum will suck the curtain onto the person having a shower. And also we have the Coanda effect. If we place a teaspoon, the round side of a teaspoon, the bulging side, in a water jet, due to the rounded shape, the bulging shape, the speed will increase locally, creating a vacuum, holding the teaspoon in the water jet. Now, let us look at an airplane wing with an asymmetric cross-section, and if we place it in an airflow, we see that the wing, the airplane wing, will disrupt the airflow. Locally, the speed above the air wing increases because of the flow conservation law, and therefore pressure decreases. If we take two air molecules on the attack edge of the wing, the one that goes above will have a longer travel and will go faster than the one at the bottom in order to meet at the end. There is local speed increase above an air wing and vacuum. The vacuum tends to drag the wing profile upwards, and this is the reason why planes take up. We understand that vacuum forces above the wing will be greater than the pressure forces under the wing. A few things you need to know about the profile. The attack edge is the one at the front, the trail edge is the one at the end, and the distance between the two is also called the chord line. The upper surface and the lower surface are also to be considered. Now, if wind arrives on the wing with an I incidence versus the profile axis, the airflow going above the wind will gather speed and create a vacuum, generating a lift force. And the lift coefficient is CZ, and there will be a sustentating effort. And if we place something in the airflow, this will cause a drag force, and the drag force is Cx. When the profile is symmetric, we see that if small I equals 0, the two courses up and below, on top and below the wing are the same, so the lift force and the trail force are equal, and the lift force is 0. We understand the same thing on the next graph. How do we obtain this? Either we use wind tunnels or virtual wind tunnels on the internet, and if the incidence angle is 0, lift is low and there is 0 and there is very little trail. And if we increase the incidence, if we reach an incidence angle that is common to all profiles, 10 to 12 degrees, lift will drop and drag will increase strongly, and this is because the boundary lines go above the profile, causing a vortex. This is very bad for an airplane if that should happen, because the airplane will simply crash to the ground. But for wind blades, this property is used to slow down the windmill rotor. Before we close, these pictures show you the vortexes above a windmill blade or an airplane wing. Very close to the stalling point, we see the vortexes being caused when we go above the stalling angle. Thank you.